algebra. We are continuing in PO61, part 1 of 3. Damien, warning for you. I feel like that's just like routine now. So where we are simplifying these square roots. So we talked yesterday about how a calculator will only help you to a point on this test. It can help you check answers, but as far as getting to the answer, you need to rely on your knowledge of factors and perfect squares and how to simplify these. We did the first row together. So let's just pick like 2 from these next 8 so that you have a chance to practice yourself, and then we'll talk about fractions and things like that. So give me one from the second row that you'd like to do. Lisa. Root 54. So refresh my memory here. What are we looking for to simplify? Remember, to simplify means you keep the exact value. We're not rounding. We're not estimating. We can't evaluate because it's not a perfect square. What are we looking for, Anthony? All right, Joey. Yep, we're looking for a factor pair.
And one of the factors is a perfect square.
Right, and one of those factors needs to be a perfect square. For 54, what's that factor pair? Who already knows it? Catherine?
9 and 6.
Yes. Okay. Now there are other factor pairs of 54, right? 18 and 3, but 18 and 3, no perfect squares. 27 and 2, 27 and 2, no perfect squares, right? So 9 and 6 is the one that we want. It gets us that perfect square, and we want that perfect square because now what can we do with it? Simplify it, okay? Or we can evaluate it actually, right? Root of 9 equals 3. The root 6, we don't know, we don't care. 3 root 6 would be our final answer. And then go back and check this. Plug in root 54 in your calculator. Get like 7.3, 7.4-ish. And then put 3 root 6 into your calculator, and you'll get the same never-ending, long, nasty decimal. Okay? Pick one in the next row. Jack.
104.
104. What's a factor pair of 104 that contains a perfect square?
26.
Okay. What's that?
26 isn't a perfect square.
26 isn't, but
4
is, right? And so part of this is, you might not know all your factors of 104. It's not really a number you use too often. But remember, since we want one of those factors to be a perfect square, you're basically checking if 4 goes into the number, or 9, or 16, or 25, or 36, right? It's not a long list of factors that you're checking. Check 4 first. 9 is easy to check also. You should tell if 25 can go into a number, right? So it's not like you're starting from scratch on what factor pairs you're trying to find here. You do want one of them to be a perfect square. So root 4 times root 26. Root 4 becomes a 2. Root 26, don't know, don't care. We cannot simplify root 26 any further. It doesn't have any perfect square factors. Yesterday, the question was, will this extra root always be a prime? And in the 2 examples that we've done, no, right? But the problem is 26 doesn't have any perfect square factors. So you cannot go any further. 6 has no perfect square factors. So you cannot go any further. Okay? Let's have one of the fraction ones. So there's a cool property involving roots in fractions. And that, for example, the root of 27/16 can be rewritten to be the root of the numerator over the root of the denominator. Okay? So the root of a fraction can be rewritten to be the root of the numerator separately over the root of the denominator separately. And how does that help us tremendously here? Kylie?
16 is a perfect square.
Well, first of all, 16 is a perfect square. We can evaluate that. And then what do we do with the root 27? We don't leave it because we can simplify it. What's our perfect square factor pair? I like that. Perfect square factor pair. I feel like there's a song in there somewhere. That rhymes too. Christopher.
9 and 3.
9 and 3. Okay? So we get root 9 times root 3. The root 9 becomes a 3. And so our final simplified expression would be 3 root 3 over 4. Okay?
Yeah.
Well, fractions always make things a little bit more complicated. But when you break it up into its separate roots, you don't have to deal with the fraction as a whole. You can deal with each individual root separately. And the fact that one of them is a perfect square, well, that's just the spirit of Christmas. Okay. All right. Any questions on your brief review from yesterday? All right. Yes, Damien.
Can you say it's your new and improved song?
I'm working on it. You know? Yeah. In the next, 8 minutes or so with the people around you or individually, work through the rest of this page. We'll go over answers, we'll talk about it, and then we'll move on to page 2.
Hey, Kristen.
Here we go. All right. Going over some answers from what you did on your own. Raise your hand if you can confidently tell me what the root of 125 simplifies to be. Kylie.
5.
5 root 5 is what you should have. You get that from the factor pair. 25 times 5. Root 108. Confidently. Liesel. 4 root 27. 2 root 27. Okay. I wrote it up and to the right because
Simplify it.
we can simplify root 27 further, right? Which means that we did not choose the largest perfect square to start with. 4 times 27 gets us 208, but there's a larger perfect square that goes in 108 as well. Sophie?
3 root 10.
So 9 times 12. We could simplify that 12 further because it's got a perfect square factor as well. So there's even a bigger number that goes into 108. 36 and 3. Yeah, 36 and 3. Okay.
What about 64 and 2?
64 and 2. That's 128, not 108. So this is that situation, right? Where when you're done, look at that root and ask yourself, is there a perfect square factor that I can take? I'm not even recording right now. I mean, I am, but my microphone isn't even turned on. Oh, that's a lot of dead air right there. Hi, everybody. We're back. So anyway, I am better than that. So always look at that leftover root and ask yourself, is there a perfect square factor that I can take out of that? So this is the one we want. 6 root 3 should be your answer. 6 root 3. And if you got 2 root 27 to start with, remember you can then take this. You can break this down into root 9 times root 3, which becomes 3 root 3. And then original 2 times that 3 gives you 6 root 3 as an answer anyway. So you can still get there if you don't pick that largest perfect square, but it does take more steps. Root 363. What'd you get for that one? Root 363. Rowan.
11 and root 3.
So 121 and 3 is the factor pair. So 11 root 3 would be your answer. And as one of you astutely pointed out yesterday, we can put it there as well because my former editor put the same question in there twice. Liesel, root 27.
3 and root 3.
3 root 3, which makes sense. That's what we got down here when we simplified root 27 there. Root 250. Ellen. 5 root 10. 25 times 10 gets us to 250, and 25 is the largest perfect square. So 5 root 10. Now down to our fractions. We can start by splitting this up into root 50 over root 21. 121, thank you. Which is a perfect square, so our denominator ends up being, Joey? 11. And then how does root 50 simplify? Kylie?
Root 25 and root 2.
Root 25 times root 2, which gives us 5 root 2 as the final answer there. So 5 root 2 over 11. Root 80 over 25. Again, we can split this up to be root over root. That denominator is a perfect square. You're welcome. And how does root 80 simplify? Catherine? Yes, you may. How does root 80 simplify? Claire? 4 root 5. 16 is the largest perfect square. 16 times 5. And the root of 16 gives us 4. Can we cancel out those two 5s?
No.
Why not?
Because one is in the square root.
Because they're not the same value of 5, right? This is the root of 5, not just 5. So you actually cannot cancel them out. Alex, you were correct. And the reason is because one is under that root and the other one isn't. It's not like an equivalent value of 5. One's a root 5 and one is just a 5. The next one, last one here, root 147 over root 64. Again, that denominator is a perfect square, gives us 8. And root 147 simplifies to be, something I haven't heard from yet today, perhaps. Noah.
7 to the square root of 3.
So 49 times 3 is the factor pair. 49, root 49 is 7, so 7 root 3 over 8. Okay. Questions on any of this? This is where everything else in this unit stems from, right here. Okay? So if you are having questions on how to do this, those questions are going to continue to plague you all throughout the unit. So now would be a great time to ask your questions. Maybe it's just a matter of brushing up on your perfect squares, right? If you're having trouble finding, if you know what to do for having trouble finding factor pairs, write these numbers down, right? And just brush up on those perfect square factors. Damien.
So, is your main priority when you get to school to do the word so everybody can talk to you? I've never seen that sheet change.
I usually do it before I get to school. Yesterday, I was doing it during homeroom. It was a math day, so you weren't here. But I usually do it when I wake up in the morning or when one of my kids.
Geez, wow.
Thanks for keeping us on topic here. Appreciate that.
Yes.
Okay, moving on then. Because of course, we always start with numbers, then we introduce variables.
They are letters.
But you actually are at an advantage here because you are all PERMDAS people, and you know just you know what this means here. You know what the root of x squared equals because you know that a square root will cancel out. It's the opposite operation of squaring something. In fact, you've done this before, right? When you had something like x squared equals 9, what did you do to get x by itself? You took the root of both sides. So, what does the root of x squared equal? It equals x. Okay? It equals x. The root symbol and the power of 2 cancel out, opposite operations, and you're left with x. Basically meaning that x squared is a perfect square, right? X squared is a perfect square because we know, what does a perfect square mean? The root of 9 is 3 because 3 times 3 equals 9. The root of x squared is x because x times x equals x squared. Okay? The understanding of how to deal with roots in variables is an understanding that any variable squared is a perfect square. Part of it is because of opposite operations. The other part of it is the mere definition of what a square root is. Okay? So hang on to that. The root of x, we can't do anything with because we don't know what x equals. So we cannot simplify that. So the root of a variable by itself isn't going to change. That's like that extra factor that you can't do anything with. We don't know, we don't care. Root of x is just going to stay root x. Root of x squared simplifies to be x. And now when we get to the root of x cubed, just like how we want to break up a number into its 2 perfect square factors, how can we break apart x cubed into 2 factors, one of which is a perfect square? Max?
You would do x squared and then just x.
Is it not correct that the root of x squared times the root of x would multiply to be the root of x cubed, just like the root of 9 times the root of 5 would multiply to equal 45? Follow me? Right? We just finished 2 units about dealing with variables and exponents and multiplying x squared and x cubed and all those things together. Do you see how a factor pair of x cubed, meaning two things that multiply, right? X squared times x equals x cubed. Any argument there? Oh, let me get through this first. Any argument that x squared times x equals x cubed? You have an argument? Then put your hand down. Okay? Right? Now, we broke this up into these two factors because what's true about the root of x squared? It's a perfect square. The root of x squared equals x. And can we do anything with that root of x? Do we care? No. So the root of x cubed is equal to x times the root of x. This x comes from that perfect square factor. And that root of x is like that root 5 here, right? This root x squared is like the root 9. It's a perfect square factor of 45. We can simplify that. The root 5 is like the root x. We can't do anything with it. We don't care. It just takes long. Okay, Elliot, go ahead.
So we did PEMDAS in middle school.
That's why you transferred.
We did
What?
PEMDAS.
Isn't that why you transferred?
No.
So,
Like, what's
PERMDAS is like PEMDAS.
Parentheses,
Better.
exponents,
Because
radical.
PERMDAS has the R, which stands for, everybody? Radical. Because when we look at the order of operations and look at it in terms of opposite operations, right? A and S, addition, subtraction, opposites, right? MD, opposites. PEMDAS people, I feel sorry for it. The PEMDAS people, they get to that next level, right? And like, what's the opposite of an exponent? I don't know. PEMDAS doesn't tell me. That's why we got PEMDAS. Because the root undoes the power. What's that, Ron?
What's the opposite of parentheses?
Parentheses isn't an operation. It's a grouping symbol, so it doesn't have an opposite. So it's not an operation, right? You can't parenthesize something. You know, you can put something in parentheses, but you can't parenthesize it. You can add things, you can multiply things, you can't parenthesize. Alex.
Can you put this on a help sheet? That's the key of it.
It is a key point. That's a very good point to make. Damien.
Did you come up with PERMDAS?
No. I wish I did, though.
Are we the only school that does PERMDAS?
I don't think so. Epiphany also does it.
The other good
Because I
schools.
taught there before. Claire.
So your why wouldn't it just be like x to the 0th power because there's two x's and then like you take the 2 off? So why is it just an x?
You don't take the 2, well, you take the 2 off, yes, but the reason why it's just x is because go back to the definition of what a square root is. It's what times itself equals whatever's under the root, right? The root of 9 is 3 because 3 times itself equals 9. So when we take the root of x squared, what we're looking for is what times itself equals x squared. That's where x comes in. Because x times itself equals x squared. Therefore, the root of x squared is equal to x. Okay? It's kind of, I mean, it's similar to like if you start with x and you multiply x by 3 and then you divide by 3, you're left with x, right? That opposite operations, you multiply by 3, you divide by 3, you've got x by itself again. If you square x and take the root of it, those cancel out and you're left with just x. Okay? Moving on to the root of x to the 4th. I'm going to write this out kind of longhand here. What can we take out of root of x to the 4th? What factors can we pull out of x to the 4th? Liesel? You mean like x squared times x squared?
Yeah.
Ah, okay. Right? X squared times x squared equals x to the 4th. What do we know about the root of x squared? It's a perfect square. So each of these canceled out. They cancel out for 2 reasons. A, they're opposite operations. Roots and exponents, they to each other, right? And number two, what's the definition, again, going back to the definition of a square root. What times itself equals what's under the root? What times itself equals x squared? X does. That's why the root of x squared is just x. Okay? So each of these root of x squareds gives us a what? An x. And how can we combine those? X squared. Max?
Can't you just, whenever you have an even power, just divide it by 2 and that's the answer?
We talked yesterday about if you have two perfect square factors. I think Lisa will ask the question yesterday. What if both of your factors are perfect squares? What did I say? If both your factors are perfect squares, what does that mean about the original number? It was a perfect square to start with. Both of these factors are perfect squares. Therefore, the root of x to the fourth is a perfect square to start with. Because what times itself equals x to the fourth? X squared times itself equals x to the fourth. So Max now wants to jump down to x to the sixth here. What times itself equals x to the sixth? X cubed. What times itself equals x to the eighth? X to the fourth. What can we say is true about any variable to an even power? Claire, go ahead. Say what you can say.
Does that mean for an odd number you just put like the square root of x and then divide that one by
You're
2?
close, yes, but let's finish this out first here. What can we say about the root of any even power? It's a perfect square. Okay, because we can take out all these x squared, right? X to the sixth we can factor out to be x squared times x squared times x squared. We can take out 3 perfect square factors that give us x cubed as a simplified expression. Max also said the shortcut, I believe, if you have, say, for example, the root of x to the 70th, how could you very quickly, easily, efficiently, why?
That's what I was gonna say.
The shortcut is, yep, divide the exponent by 2. Okay? When you have the root of an even power, the exponent is just cut in half. Because that's how many x squareds can go into the original power. What's that?
The other questions are gonna be hard.
What other questions? Like down below?
Yeah.
Don't look down below yet.
Too late.
Keep your eyes up, Damien.
I already did 2.
Eyes up.
I already did 2.
Alex.
It's 2:15.
Okay, so now we go back to those odd powers, right? Okay. What do you suppose the root of x to the fifth is going to be here? Claire touched on it. Claire T?
X to the third, or x to the third times x squared.
So x to the fifth, we can break it out to be x squared times x cubed. But I'm going to go one step further. What's the largest perfect square that we can take out of x to the fifth? We can take out an x squared. What's the largest perfect square? X to the fourth, right? We already established that x to the fourth is a perfect square. So we can take out that x, we can factor out that x to the fourth and multiply by that root x. That gives us x to the fifth. Arlene?
Wait, so the answer is x squared and then the square root of x.
So the simplified expression is x squared root x. Digest that a little bit.
Oh, I get it.
Okay? Digest that a little bit. Right? Variables are really, they're different from numbers, yes, but they have the same properties. Don't let it fool you that it's an x versus something else. Our goal here is take out a perfect square factor from x to the fifth, because we know that any even power is a perfect square, we can take out an x to the fourth. That's our perfect square. That gives us x squared. And the root x is just left over. Claire.
So it's basically you subtract 1 from the exponent and then divide by 2.
And you'll have that extra root x. Yeah. What's the perfect square factor we can take out of x to the 7th? The largest perfect square factor we can take out of x to the 7th. Damien?
X to the 6.
Well done.
X.
Right? We've established that x to the 6th is a perfect square because it's even. We can take that out of x to the 7th and we're left with that leftover root x. So what's our simplified expression?
X to the 3rd.
X cubed
Oh yeah.
root x.
Oh, that's the next one.
Yay, math. Okay? So we have a pattern here, right? If we increase our exponent by 1 and look at our final expression, we've got root x, x root x squared root x cubed root x to the 4th, right? What would x to the 9th simplify to be? X to the 4th root x. Okay? For an odd power, you'll always have that root x taken on at the end. Claire said what the rule is, when the exponent is odd, subtract power by 1, then divide by 2. Right? And then you'll always have that extra root x hanging on. Okay? The actual, formula for it, I suppose, would be your answer would be x to the n minus 1 divided by 2 root x. Basically, what this means, subtract the power by 1 and then divide by 2. Whatever your power is called n, right? Subtract that by 1, divide by 2. It looks more complicated than it actually is. This is the verbal of it. Subtract the power by 1, then divide by 2. If that makes more sense, don't write this, right? But either way, that's what's happening. Okay? That's what's happening. Next.
For on the bottom, like 15x cubed, there you can't simplify it down to perfect square.
Fine, I'll go down to the bottom. Any more questions on this top part, though?
No.
Wait, what does that say?
It's a lot to take in, right? I don't expect you, I promise you'll get a lot more practice with this as we go on. If you get the base, if you get the gist of it, though, that's good enough for right now. Okay? It's good enough for right now. So Max, you wanted to go down to where?
Right there.
The 15x cubed.
Oh, you're going to start with a fraction? That's what you want to do?
Yeah.
All right.
Why would you like X squared?
Well,
We hate fractions. We very much hate fractions.
all right. So we know that based on what we talked about earlier today, we can split this up into the root of the numerator over the root of the denominator. Okay? So we don't have to deal with the whole fraction as a whole. We can separate it into its parts. Let's deal with the denominator first. Root 4y squared. We can rewrite this to be the root of 4 times the root of y squared. And what do we like about the root of 4 and the root of y squared? Rowan, what's the root of 4?
2.
What's the root of y squared?
Y.
Because I asked. So our denominator simplifies out, right? The root of 4 is 2. The root of y squared, because that power is even, right? Just becomes a y.
Yes, sir.
The root of 15x cubed, we can split this up to be the root of 15 times the root of x cubed. Can we do anything with the root of 15?
No.
No perfect square factors.
No.
What does the root of x cubed simplify to be? Damien?
The x squared.
Subtract the power by 1, divide by 2,
Never mind.
It's also in your chart up
X
above.
squared and then X.
Alex?
X.
You said X.
X root X. Okay? Subtract the power by 2, divide by 1, that gives you X to the first, or just X. And then since the power's odd, we know we'll have that extra root X hanging on there. Okay? So to put this all together, outside of our root, we have an X. Inside of our root, we have a 15 and an X. So X root 15X over 2Y would be our simplified answer. Remember, it was not my idea to start with this one, okay? Just let's make that clear. I didn't pick this. Elliot.
Well, actually, the square root of 15 is 3.872983346.
If you would like to write out that irrational number as an exact answer, you'll need a bigger calculator and a lot of paper. Because the root of any non-perfect square goes on forever. It's an irrational number, it will go on forever.
If we got it like that, would we get extra?
But I'm not one to trample on one's dreams. So if you would like to write the exact value of root 15 as a decimal, here's paper in the back. Yes?
How do the mathematicians figure out that a perfect non-perfect square goes on forever? Did somebody
created math.
Because you couldn't stop dividing it.
So
Somebody's
the calculation to figure out like how it started, right? Take 15, okay, and folks are like, all right, what times itself equals 15? Well, 3 times 3 is 9. 4 times 4 is 16. So it's got to be between 3 and 4, right? 3.1 times 3.1 is whatever, right? So they kind of narrow it down. And eventually computers came into play and they do all the work for us. But kind of like how they first discovered what pi was. You know, pi was originally 3. And then folks are like, well, that's a little bit more than 3. Right? And it's like 3.1. Well, it's a little more than that too. 3.2, a little bit less than that. You know, very early is kind of narrowed it down.
It doesn't go on.
It does go on forever. Despite what your Google calculator says, Alex, it goes on forever. Not even Google has enough bytes to put every digit of an irrational number in there because irrational numbers go on forever. All right. Are we doing okay?
No.
I'm not going. Don't go by this one. Again, I didn't pick this one as a first example. If you can, like that one, that one, that one, that one, that one. Okay. No homework for tomorrow. We'll pick this up Monday. Tomorrow will be a retake day. How do you do this? That one? You split this up to be the root of 8 times the root of x squared. You split it up to be the root of 8 times the root of x squared, and then simplify each side. Sorry? Yes, it's basically what we did here. Yeah. All right, folks, so long. Have a nice day. Like and subscribe.